So in today's lecture, we are going to talk about Wick's theorem. So in a previous lecture, we stated without proof that all observables in quantum field theory can be derived from, so in this expression, this is omega, these are the interacting vacuum, this is the ket and this is the bra, and this is the time ordering operator, and phi1, phi2, dot phi n are some general operators, and x1, x2, xn are their arguments denoting the points in space-time. So presently we are considering the phi to the power 4 theory, and there, we shall take this expression to be in other words, we are taking all the phi's to be the same thing. It could also be that instead of phi, we get pi sometimes, because pi is the canonically conjugate momentum, and that's related to phi in this way. Anyway, but for now, we'll just consider this expression. So what we saw in a previous lecture is that how we can express the interacting vacuum in terms of the free vacuum and how we can express the Heisenberg operators in terms of the interaction picture operators. And in the interaction picture operators, they have a much more simple expression in terms of a Fourier integral. So although we worked out what the perturbative Dyson series expansion of the 2-point function will look like, it is just a straightforward exercise to generalize that to the endpoint function. So the endpoint function is the vacuum expectation value of n Heisenberg operators. So it's given by this. And note, we saw that we can write this as taking the limit of time going to 1 minus I epsilon times infinity. And then in the denominator, we have the free vacuum, and then the time-ordered product of the interaction picture fields. And then we have the time evolution operator in the interaction picture, which we can express as a Dyson series. So there's a time ordering operator here. So the Dyson series will look like this goes from minus t to plus t. So here we have d of t, hi of t. So this is the numerator. And in the denominator, we will just get the time evolution operator. So here we also have the t, the time ordering operator. So this is the expression for the endpoint function. So in this expression, by hi of t, we mean the interaction Hamiltonian in the Heisenberg picture, in the interaction picture, and that's a function of time. So what we have done is that we have expressed all the endpoint function in terms of products of the form of time ordering of a bunch of the interaction picture operators. because that is what we will get when we expand this exponential and this time order exponential. We'll just get, terms of this form and with some integrals over them. So in order to evaluate these things, we will first of all need Wick's theorem. And what does Wick's theorem do? Wick's theorem expresses time-ordered products of operators in terms of normal ordered products and Feynman propagators. So to prove Wick's theorem, we will need a little bit of notation. So let's take the interaction picture operator and express it as a Fourier integral. As we saw in the last few lectures, the interaction picture allows us to express the operators as Fourier transform whose form retains its, as we saw in previous lectures, that in the interaction picture, the fields can be expressed as a Fourier integral, which coincides with the expression for the free field theory, even though we are not dealing with the free field theory. So here we are going to, the first term has the annihilation operator and the second term has the creation operators. And we're going to write this as two different terms. So the first term I will call phi I plus of x, and the second term will be called phi I minus of x. So in other words, phi I plus of x contains the annihilation operator. So we have dk tilde a of k e to the power minus kx. And in the business, this is called the positive frequency modes. The positive frequency modes. While on the other hand, phi I minus of x has the form a dagger, integral over a dagger of k, e to the power I kx, and in the business this is known as negative frequency modes. So these names are historical, and it's important to keep in mind that the positive frequency mode has a negative sign here, and the negative frequency modes have a positive sign here. And the positive frequency modes have annihilation operators in them, and the negative frequency modes have creation operators in them. The names are historical, so they don't really mean anything other than being just names. Historically, people interpreted these as wave functions for positive energy states, that is particles, and these as wave functions for negative energy states, that is antiparticles. And that's where the name positive and negative came from. But since we don't give interpretation to these as particles anymore, they are just creation and annihilation operators. Therefore, they do not have interpretation of being having any particular energy. And that's why instead of energy, we now use positive frequency and negative frequency in the names. Anyway, that's just a historical side note. So now let's consider the time order product of two interaction picture operators. So I get t phi I x and phi I of y. So let's consider the case, let's call it case 1, in which x0 is greater than y0. In that case, this guy, t of phi I of x and phi I of y is automatically phi I of x, phi I of y. And that's because x0 is in the future of y0, and this is time ordered. So now what we can do is that we can just expand these operators in terms of their creation and annihilation operators, that is the positive frequency modes and the negative frequency modes. So the first operator is phi I plus x plus phi I minus of x times phi I plus of y plus phi I minus of y. And now what we will do is that we will try to reorganize these terms in normal ordering form, of course, keeping track of their commutators. So first, let us just multiply them through. And if I multiply them through, I'm just going to drop the I subscript for now because everything here is in the interaction picture anyway. So, and also I'm going to drop the brackets here. So I'll take some shortcuts. I hope you don't mind. So the first term is phi plus, and it's at point x. And then phi y at point y, phi plus at point y, and then phi x plus phi y minus. Be careful, this is a plus, not a dagger. And then we have phi x minus phi y plus, and then I have phi x minus phi y minus. So now we have four terms. We see that both of these terms contain creation operators because that's what we have here. The minus have creation operators. So this is already normal ordered. This has a creation operator in this operator and an annihilation operator is in this operator. Therefore, this is also normal ordered. And this is also normal ordered because they all both contain annihilation operators. However, this term is not normal ordered because this has creation annihilation operator, this has creation operators. So we have to do something with this term. So what we do is that we keep all the terms as they are, but for this term, we subtract the normal ordered term. But of course, since we subtracted it, we have to add it as well. And then we have the rest of the term that were already there. So, and then we can write, so there's a lot of repetition. And this we can write as a commutator. And because it's a commutator, it's going to be a C number, meaning this will not be an operator. This will be just some function. And then we have the other operator terms, which are all normal ordered. And it's easy to see that all these other terms, these four terms, can be written as the normal ordering. So, we can also use this notation for normal ordering. So the normal ordering of the phi x, the operator at x, times the phi y operator plus this term, which is, I'm claiming, is just a C number. It's not an operator. Of course, we can always put the identity operator here. And because of that, because the fact that there's neither a creation operator nor an annihilation operator, we can just extend the normal ordering to include that term as well. So we can write this as phi x, phi y, plus the commutator of phi x plus and phi y minus. So this is what we have when x0 is greater than by y0. When y0, which is the case B, is greater than x0, just a parallel computation just tells us that phi I of y, phi I of x is going to be the normal ordering of, again, the same thing here, but here in the commutator, we will get phi y of plus and phi y of minus. So now what we can do is that we can define the contraction of two fields, phi x and phi y. We call it a contraction. And it's a number, and it's symmetric in x and y. And this is, we define it to be the commutator of phi x plus phi y minus if x naught is greater than y naught, and it's phi y plus phi, sorry, this should be x here, phi x minus if y naught is greater than x naught. So in other words, what we're saying is that phi I of x and phi I of y, the contraction is theta x naught minus y naught times phi x commutator phi x plus phi y minus plus theta of y naught minus x naught commutator of phi y plus phi x minus. Now, I've claimed that this is just a C number. It's not an operator. But what is it? That's very easy to work out. So what we do is that we just take the commutator. So let's just work this out. Phi x of plus, phi y of minus. So we should get two integrals. So we get dk1 tilde, dk2 tilde. And inside, from this guy, I'll get annihilation operators, which are a of k1. And from this guy, we will get creation operator, which is a dagger of k2. And then from these two things, I'll get some exponentials, which is e to the power minus I k1 x plus I k2y. And then we can use the usual commutation relationships, and we can find dk1 tilde, dk2 tilde, and then I'll have 2 pi cubed 2 e of k1 or 2, it doesn't matter, a three-dimensional delta function between k1 and k2, and then we'll get the exponential of e of I minus IE k1 x plus I k2x. Now, using the delta function, we can do one of these integrals, and those, of course, these measures contain factors of 2 pi cubed as well as this guy, so that'll cancel out. So I'll end up with only one k integral, and k1 will become equal to k2, and therefore I will get minus I k x minus y. So this is what this guy is. On the other hand, if I look at phi y of plus and phi minus phi x of minus, then it's easy to show just by using a similar calculation. It's dk cubed e to the power minus ik y minus x. So therefore, what we have shown is, if you go back and compare the expression for the Feynman propagator, what we have shown is phi I of x, the contraction of phi I and phi y, is nothing but the Feynman propagator. So having shown this, we can write our expression for the first Wick's theorem, so the time ordering product of two interaction picture operators, phi I x and phi I y, is given by the normal ordering of phi I of x, phi I of y, plus the contraction of phi I of x, phi I of y, but this we are claiming is the Feynman propagator. So this is known as Wick's theorem for two operators.